All right, then let's get into it. So last time, what did we talk about? We did this like linear systems review stuff. That was mostly about kind of stability of linear time invariant systems. Then we talked a bunch about group theory and Lie groups, which hopefully that was kind of interesting and new for you guys, and probably we'll do a little bit more of that stuff. Then we talked a bunch about rotation matrices again and sort of their kinematics. And then we started talking a little bit about quaternions. In particular, we sort of did this geometric picture, right, with like how you kind of construct them and copying and spheres and stuff. Okay, cool. So today, if anyone has any questions on any of that stuff, now's the time. Okay. So today we're going to do kind of like finish the quaternion story, or at least, you know, the first version of it. And then we're going to talk about kinetic energy of a rigid body. And then we're going to sort of use that as a segue into defining inertia, inertia matrices, inertia tensors for rigid bodies. And then we're going to look at Euler's equation, which is sort of the F equals ma of rotation dynamics for rigid bodies, right? So who's seen Euler's equation before? Like most people, half-ish. And I think, yeah. Okay, cool. Let's get into it then. So quaternions part 2, or sort of the main part. So last time we looked at this geometric picture, which I will attempt to draw again. So we have like this, you know, the disk popped up into the hemisphere idea. And then we make a copy and sort of glue it on underneath, right? And then we make the sphere, and that's kind of the thing. So it turns out if you stare at this picture, you can actually derive sort of the relationship between axis angle vectors and quaternions right from this picture. So bonus if anyone wants to do that and work it out. So I'm going to write that down real quick. It's sort of not surprising. It's a bunch of sines and cosines and stuff, right? You can imagine like, you know, taking you can do it in sort of 2D by looking at a line and then sort of popping it up into a circle and stuff, and then kind of extrapolate how that looks. So we get this. So the quaternion is going to be this 4D thing now, and I'll write it down and then we'll talk a little bit about it. So here in this thing, we call the top part of this the scalar part, because it's a scalar. We call the bottom part the vector part, because it's a 3D vector. And the theta here is the sort of the angle in radians. So it's like norm of phi if phi's our axis angle. And then the r here is the unit vector axis of rotation. So this would be like phi over norm phi. So yeah, bonus points if anyone goes through the exercise of deriving this from the picture. And let's see, what else is there to say about this? Okay, so a few notes. First one is, by looking at that thing, because of the sine and cosine, if I wrote down Q transpose Q, right, if I square that thing, it's going to end up having a sine squared plus cos squared equals 1 kind of thing going on. It's really easy to show that. So these are always unit 4D vectors. We call these unit quaternions. So you can have non-unit quaternions, but they're not rotations. Unit quaternions correspond to rotations. Non-unit quaternions correspond to like a rotation plus a stretch. So they're sort of a different thing, right? So that's important. So one of the big reasons why these are preferable to rotation matrices is that these guys, if you get numerical error, numerical drift kind of stuff happening, and this is question 2 in the homework, you're going to play with this. These guys will drift, right, due to numerical round off and stuff in your integrator, and this will get violated, but it's super easy to renormalize, right? I just like, normalize a vector. The rotation matrix case is a lot nastier. So if I do the same thing with a rotation matrix, it's going to drift away from an orthogonal matrix, but it's a huge pain to renormalize that thing, relatively speaking. So this is one of the reasons that these are good for a simulation. Okay, another fun fact that shows up here. What happens if I plug in theta equals 2 pi? So if I have theta equals 0, cool, I get an identity thing. If I plug in theta equals 2 pi, what do I get? I get like a minus identity thing, right? So this is weird, right? Because 2 pi is a full rotation and I'm back where I started. So it turns out here, there are two, unsurprisingly from the picture, there's 2 quaternions for every rotation. We call this a double cover. So Q and minus Q correspond to the same rotation matrix. These things are 4 pi periodic instead of 2 pi periodic. There's some stuff the other time with the spin group spinners. That's what this is all about. This double cover thing, this is called the spin group. If anyone's heard of this, fun. If you've taken quantum mechanics before, these are polyspin matrices. If you heard of that before, I don't know. I was a physics undergrad. Okay, so Q and minus Q correspond to the same rotation. This is called a double cover of SO3, the rotation group. It's a little weird. It's a quirk. So this is basically the one major quirk about quaternions versus rotation matrices. They don't have any singularities. They're nice and smooth and well behaved, and they're easy to work with computationally. But they have this double cover quirk, which can get you in trouble in controllers. So if you write an attitude controller or some kind of controller that uses the quaternion, you have to sort of take care of this. Otherwise, you can get weird behavior. It's called, there's this thing that happens if you do a naive controller called the unwinding phenomenon, where you can do a 2 pi rotation for no reason, essentially. If you're sort of not accounting for this Q minus Q thing, you can like end up at minus Q and you want to be at Q. If you're naive about this, you'll do a full 360 for no reason in your controller. So just be aware of that. It's not sort of what we're mainly talking about here. For simulation, it doesn't matter at all, right? Okay, cool. And again, yeah, this is obvious from the geometry. We made a copy, et cetera, right? Okay, cool. So the main takeaway from here that I want to like get across before we go into what I'm going to just kind of blaze through a whole bunch of quaternion fun, math stuff just really quickly. The main thing I want to just say before we do it is that everything about quaternions is analogous to rotation matrices. So when you're working with them, just like squint and pretend they're matrices, then everything works and everything's literally, remember the whole thing about like isomorphisms and groups and all this stuff? These act the same way as rotation matrices under their multiplication rules, inverses, blah, blah, blah. So if you just kind of like, pretend they're rotation matrices, when you work with them, like life will be fine and you can kind of swap them interchangeably. Okay, let's see. So that's the last thing from here. Modulo a few quirks due to the double clever thing that we'll point out. Okay, so who's worked with these things before? Half-ish. Okay, yeah. Okay, so here we go. So things to know. First one is quaternion multiplication. And I'm going to do this a very particular way that is sort of the Zach way that is not maybe what you've seen other places, but it's going to set us up for doing some fancier things with these later on. So first off, here we're going to define the rotation. This is standard. So we've got this scalar part, vector part. I'm going to use this kind of star, asterisk, whatever for quaternion multiply. So here, these two guys multiply together. Here's what it looks like in terms of the scalar and vector parts. It's scalar, scalar minus dot product of the vectors up top, and then scalar vector plus scalar vector plus cross product of the vector parts. As a fun historical aside, these were actually invented before the standard vector dot and cross products, and they sort of subsume both of them, right? The classic dot and cross products show up in here. So this sort of like combines them both in a kind of interesting way. These were invented by Hamilton, same guy as Hamiltonian dynamics and stuff. And then the standard dot and cross product things were invented by Gibbs like later as a simplification of the quaternion stuff, because people were super freaked out by these because they were 4-dimensional, and that weirds people out a lot. Okay, cool. So there's this thing. What we're going to do next is the non-standard thing that is super useful, though, in my opinion. So what I can do from this thing, I can pull out from this expression, I can pull out, I can turn this into a matrix vector product in two different ways. So I can pull out the Q1 stuff into a matrix that looks like this. And this is that cross product hat thing from before. And so it's this thing times Q2, right? So we're going to call this L of Q1 for left-hand multiplication. So this lets me write all the quaternion stuff in terms of standard matrix stuff, right? That's kind of what we're going for. And this is like way less ambiguous and way easier to deal with when you're doing stuff in a computer and when you're trying to do calculus with these things. If I need to take derivatives, this is the way to do it. Okay, so this, I can also pull out the S2 terms into a matrix. So I'm going to get S2, or sorry, the Q2 stuff. And here I'll get S2 identity minus V2 hat, and then minus V2 transpose up top times Q1. So this matrix we're going to call R of Q2 for right-hand multiplication. Someone see that? So it's literally just me looking at this thing and pulling out, you know, into a matrix out front, you know, the Q1 terms here or the Q2 terms here. Is that sort of clear, everybody? Yeah. And they're only different. This is the only thing that's different about them, right? So they're almost transposes of each other, but not quite. This is useful if you want to diff this expression with respect to one of them, right? So if I want to take the derivative of this with respect to Q1, it's this guy. If I want to take the derivative with respect to Q2, it's this guy, right? Okay, cool, which we're going to do later. Okay, so that's fun and straightforward. And you can also derive this stuff from the picture as well, which is kind of cool, but a little bit involved and takes a while, so we're not going to do it. Okay, so next thing, quaternion identity. This is pretty trivial. If I just plug in theta equals 0 into that thing from before, I'm going to get, you know, cos 0 and then like, you know, sine 0 down here, which is going to be 1, 0. So that's the identity quaternion, right? Just like the identity matrix. The next thing to talk about is the quaternion conjugate, which is denoted with a superscript dagger, which is very evocative of the transpose for matrices because that does the same thing. So we call this Q dagger, and it's equal to S minus V. So I flip the sign of the vector part. This is analogous, by the way, to complex numbers, right? Complex conjugate, I flip the sign of the imaginary part. So you can think of this as real and imaginary parts too, and it gets you this. We're going to define another matrix for this for convenience later, which will just be this guy. So it flips the sign of this guy, right? And we're going to call this T for sort of transpose. And this thing gives you the same thing as the matrix transpose. It's the opposite rotation. Cool. Next thing to talk about is rotating a vector with one of these. This looks like the following. So if I have a vector in the body frame and I want to rotate it to the inertial frame, I do this. I stick the vectors in as the vector part of a quaternion with zero scalar part, and then I do this. So I smush it on both sides with the quaternion. And this looks like the analogous thing here is if I had matrices, this is how I rotate a matrix from one frame to the other, right? I smush it on both sides with the rotation matrix. So these things, think of them like matrices, think of this like a matrix, and that's kind of what you do. You smush it on both sides. And we can also write this in terms of those L and R matrices, right? So I can do L of Q, R transpose of Q, times, this guy. I can also do R transpose, oh, sorry, I should mention here real quick, we'll do that. So I can write it either way. And this LR transpose or R transpose L thing gives you the rotation matrix, right? This is going to give you Q if you do this, obviously. So thing to note here is, yeah, I should have written this. Okay, so the whole thing with the conjugate, the dagger, it turns out that L of Q dagger equals L transpose of Q. This is easy to see from the definitions. And same thing with these guys, right? So there's this connection between the dagger and transposes. They do the same thing. So that's cool. Oh, we want to define one other thing too. So this thing where I stick the quaternion in as the vector part, or the R3 vector becomes the vector part of a quaternion with zero scalar part. That does the same thing as the hat map on matrices. So we're gonna, this is sort of a hat map for quaternions. And so we could overload the notation and do this. It acts the same way as a skew symmetric matrix, right? Because if I look back at this definition up here, it basically just does the cross product thing in there with no scalar part. So it's acting the same way as that cross product matrix. And we're also going to define a matrix H that just does this for us. So it's literally this guy. Like a 0 and an identity, right? So it's just going to take an R3 vector and turn it into this guy, which will become useful later. Okay, cool. That's simple enough. That's how you can go from quaternion to rotation matrix. Then the next thing is to talk about quaternion kinematics. So this is how we map from omegas to Q dots and like integrated gyro, like we did with the rotation matrix. And this looks like, so what we're going to do here is just look at a small incremental rotation. Or I guess, yeah. So this is going to be something like, Q prime equals Q times like a delta Q. Right? And if I assume delta Q is small, I'm going to plug it into this, cosine definition, and I'm going to take a first order Taylor expansion of that. So for small angles, this looks like, well, so it equals Q times, say, cos theta over 2 r sine theta over 2. And if I first order Taylor expand that thing, what do I get? Do a small angle approximation. So for small theta, cos theta over 2 is approximately 1. And then the bottom term is approximately, sine theta is approximately theta, right? So this is going to be r theta over 2, which is equal to our axis angle vector times a half. So 1/2 phi. where that's our axis angle. So that's the first order Taylor approximation of that thing, right? And, you know, we do a small angle approximation, right? Sorry? Yeah, so that's an axis angle vector, i.e. r times theta. We did that last time. So it's like the axis of rotation r times the angle of rotation theta. So if I do this guy, I get r theta over 2. R theta is phi. Make sense? Okay. So, so the next move is I can split this guy into an identity plus that sort of phi over 2 thing. So this is q times identity plus this thing. And I can now write that as q plus q times this guy. Okay. So now what I'm going to do is I'm going to recall like this axis angle thing. We can think about that as like an omega times a dt, right? From last time. And then I'm going to get q prime minus q, if I move that over, equals q times 0, 1/2 omega delta t. So I can pull the delta t out now and get q prime minus q over delta t equals q times this guy. And then I just take a limit as dt goes to 0 kind of thing, and I get q dot here. So I get q dot equals 1/2 q times this guy. And I can write this using our notation as 1/2 L of q h omega. So if you implement it in computer, like this is the thing to do, right? Yep.
Just a couple of lines of the extra parentheses.
Where? Oh yeah, sorry. Here we go. Better. Okay, cool. So this is pretty straightforward. It's just using the multiplication rule and like, you know, doing a small rotation and taking a limit as that thing, you know, goes to 0 with a delta t. Everyone cool with this? Pretty straightforward. It's just the equivalent of the matrix thing. It looks pretty much the same as the matrix version, right? Because remember, this is like omega hat over here, right? The only difference, rotation matrix was q dot equals q times omega hat. Here it's 1/2 q times omega hat, right? And the factor of 2 comes from the double cover thing. So essentially, if you look at all the math for comparing rotation matrices and quaternions, there's a bunch of halves that appear in the quaternion stuff because of the double cover. Everything else is basically the same. So modulo a few factors of 2 floating around, it's all the same. Yeah.
Is it appropriate to write a quaternion as a sum of 2 quaternions?
You can always do that, right? So they're just like matrices. Multiplication is a linear operator.
Yeah, so multiplication part is commutative is fine, but like the norm property no longer.
Yeah, so their rotations have to be unit quaternions, right? To be a valid rotation, it has to be a unit quaternion.
Okay, so you think that like, you can always split them, they won't correspond to anything.
So yeah, if I have a non-unit quaternion, it's not a rotation, right? It's something else. And here it's not. It's actually like a velocity thing. It's a q dot, right? So it's not. That's not a unit vector rotation. It's the derivative of one. So this is sort of okay. Does that make sense? Just like in the rotation matrix case, right? I can write down like that q omega hat thing. Like I can, you know, the omega hat is not a rotation matrix, right? It's not an element of SO3. It's something else. It's a skew symmetric matrix. So it's sort of like that's kind of the idea. That's what's going on. Yeah.
I think that's when you break up it's like the identity and then that one.
Yeah. So the identity is a valid rotation, right? Pretty much. The other term is not. What that's actually analogous to is the first order Taylor expansion of the exponential. Remember that? So it was like I plus omega hat. That's exactly what that is. I plus phi hat, right? Modular the 1/2. And I'm doing, it's exactly what I'm doing actually. I first order Taylor expanded. So this sine cos thing, that's actually the exact same thing as the Euler identity and the exponential for the rotation matrix, right? This is actually the quaternion exponential is what that is. Does that make sense? Just like complex exponential sines and cosines, real imaginary part, that's exactly what that is. And then this, I plus phi term, that's literally just the first order Taylor approximation, which I'm allowed to do here because I'm taking a limit as that thing goes to 0, right? So that's all well defined and stuff. Does that make sense?
Yeah.
Cool. Yeah.
Was H just 0, 1?
It's 0i. Yeah, it's turning the 3D vector into a pure vector quaternion with 0 scalar part, right? It's sort of taking the 3D thing and making it a 4D thing with 0 scalar part. Just like it's literally just making this out of omega.
Yeah.
That makes sense?
Yeah.
Yeah. So we're going a little fast here. It's really just definitions and stuff. There's not like a lot of profound stuff here. Right? We'll do a little bit more, and I'll just make a. Hopefully this will make a little more sense in a little bit. So we're going to talk about next, hopefully get you a little more intuition on what's going on here. So we're going to talk about the geometry of what I just wrote down. Okay, so remember these quaternions, they live on a unit sphere in R4. So here's the picture. So let's say I have Q happens to be over here. Okay? So where does Q dot live? That's Q. What's Q dot? It's a tangent vector, right? It's a velocity. It has to lie tangent to this sphere. So it lies in like the tangent plane to the sphere. So I'm gonna try to draw that. This is like the limit of my drawing skills. It's like little 3D things like this. So apologies if it's crap. Okay, so here's like this plane, right? This tangent plane, and Q dot, say, is this guy in the tangent plane, which that doesn't exactly look like it's tangent, but I'm trying. Let's try that. That looks better. So Q dot, so we've got Q dot in R4 lies in tangent plane to the sphere. Okay. Okay, so what's going on with omega? Omega is a 3D vector, right? So kind of look at what's happening when we do this. So we take omega and we sort of promote it to a 4D thing, right? And it's always in the bottom sort of 3 components or whatever. So kind of what's going on there is omega is defined to always be in the tangent plane at the identity. So you can think about that sort of from this picture as like the North Pole. So let's say I've got like the identity quaternion up here, which it depends on how you define this stuff. We'll call it the North Pole for sort of ease of explanation. So there's a tangent plane up here at the North Pole at the identity. And omega is actually just this guy up here. And I drew this the wrong way to correspond to what's down there. So I'll do this again. So we'll draw it like this way. So that's omega. It's up there at the North Pole. And then what's going on in the kinematic equation here is by pre-multiplying it by Q, all I'm doing is rotating it from the tangent plane at the North Pole to the tangent plane at Q of t, where I'm at right now. Does that make sense? And so what this is doing, the other way of saying this is when I write omega in the tangent plane at the identity, that's equivalent to saying I'm writing it in the body frame, right? Because this is the body to inertial rotation. So I'm writing omega always in the body frame, which is what a gyro gives you, right? It's strapped down to the body. So omega's in the body frame, equivalent to saying it's always written in the tangent plane at the identity quaternion in this picture. So to get Q dot at wherever I'm currently at, whatever Q I'm currently at, I rotate it down to where Q is now. That gives me the current Q dot, and then and then I integrate it, right? Does that make sense, everybody? Questions about this? Cool. All right, so So that's that picture. And then the kinematics. So that's the picture. Cool. Okay, so to give a little more intuitive flavor of this, we'll do one more thing. So this is also what's going on in the rotation matrix picture, right? I'm rotating that omega hat sort of into the right tangent plane. So little more intuition. We're going to do a quick analogy. It's actually the same stuff, just down a dimension with unit complex numbers, aka complex phasors, which maybe some of you guys have seen. So in like the 2D plane. So you can think here, right? The picture is like I've got my axes here and I've got a real axis and imaginary axis. And let's say this is like the unit circle. And I've got my Q over here, which is a unit complex number, right? And then my Q dot is up here. If I write this down, right, for a complex number, I have Q equals cos theta plus I sine theta, the Euler identity. And I can think about that as a 2D vector, right, with like we talked about last time. So I've got the real part is the X component in this picture, right? And the imaginary part is the Y component in this picture. And just like in the quaternion case, right, if this is a unit complex number, this gets me a sine squared cos squared equals 1 thing. So I get this Q transpose Q equals 1. Okay, so let's look at what Q dot looks like. So if I take Q dot equals partial Q partial theta times theta dot, which is equal to omega, right? So this is dq d theta omega. And this is the 1D case, right? If I just do that, right, and write out the derivatives here, I get minus sine cos for this guy. Times omega. And what this is actually doing, right, if I think about this a little bit, it's actually a rotation matrix, cos theta minus sine theta, cos theta, this guy, times 0 omega, right? This is like just the column here corresponding to the Y component. So it's doing the exact same thing. So the picture here is that I have the tangent plane at the identity, which in this case, the identity is right here, right, along the x-axis. So I've got this tangent plane here. And I'm writing, and omega is a vector in that tangent plane. So it's really like this guy here. And then I'm rotating it by Q up to here so that I can add it on, right? And that connection, the connection between complex numbers and quaternions is also really rich and sort of nice. It basically is complex numbers are the 2D, quaternions are just the 3D version of complex numbers. So like there's a lot of analogies there as well. You can kind of mine this for a bunch of nice intuition. You can do sort of 2D rotations with complex numbers in exactly the same way as you do stuff with quaternions in 3D. And there's correspondence between this and a 2x2 rotation matrix, right? Cool. People seen this before? This phasor idea, complex phasor things. This is a double E, classic double E thing. But so maybe some of you have seen this. Maybe not. Okay, cool. Is this helping with the picture? It's like giving you some intuition what's going on. Yeah.
So, but what about the factor of 2?
The factor of 2 doesn't show up here because this is not a double cover, right? I didn't have to do anything weird with copying and stuff for this complex case. It so happens that there's like some weird stuff that happens in 3D that doesn't show up in other dimensions and stuff. And yeah, because of it's a topological thing. Like because of like basically the odd number of dimensions in 3D, there's some weird topological stuff that happens that means I have to kind of like do the copy trick. It doesn't, it turns out you don't need to do it in 2D. And there's a one-to-one correspondence between the complex numbers and the 2x2 rotation matrices. So it's not a double cover. Yeah, yep.
So I'm trying to understand. It's a very long. So with the rotation being consistent throughout the whole.
Sorry, can you just talk louder?
Omega is consistent throughout the whole body, right? So
yep.
So what we're doing by then applying Q is to track a particular point.
No, not really. So don't think about that. It's like, think about the body has an omega. What's really going on here is so there's a body frame bolted onto the body that's rotating, right? And there's an inertial frame over here that's staying still. So if I have some constant omega, say, I can write it down in the inertial frame and it's a constant vector, right? If I write it down in the body frame, it's moving around potentially because the basis vectors are moving, right? So what I'm saying here is if I have a gyro, which I strap down to the body, it's measuring omega in that body frame, right? Cool. That's the same thing as saying like at T0, the body frame and the inertial frame are lined up, right? So it's say I just arbitrarily decide at T0, body frame, inertial frame are aligned, and then this one's going to move and this one's not, right? So I get a Q of T. So at T0, Q of T is the identity, right? So these things line up at T equals 0. And so like what's kind of going on there is omega is written in the body frame, which is equal to like, you know, if I had written it at T0 in the inertial frame, but now it's going to move around, right? And so what I'm doing here is I'm always measuring it in the body frame. But in order to like do this integration thing, I like need to sort of rotate it down to where Q of T is now in order to add it on, right? Because Q is this body to inertial thing. That's sort of, I don't know, it's kind of hand wavy. Maybe that doesn't make total sense. I'm measuring omega in the body frame. Yep. But Q is this body to inertial transformation, and it's integrating up omega in some sense, right? But I'm measuring omega in the body frame, and I have to account for the fact that like, you know, I basically have to account for the fact that like I need to sort of keep track of it in the inertial frame as well in order for that transformation thing to kind of work. This is a very hand-wavy explanation. I'm trying to give you the geometry and the algebra. Like the algebra is straightforward. I can like chain rule through this thing and just write it down. This is the intuitive picture. This is the differential geometry picture of what's going on. There's tangent planes and like a sphere, you know, geometrically. And the picture is really helpful, actually, in my experience, at least, for like reasoning through what's going on, especially when you start trying to think about derivatives of stuff. You want to think about derivatives of rotations are always in this tangent plane, and they're always 3D, just like, so omega is 3D, right? There's 3 degrees of freedom, 3D, but no matter what rotation representation I use, so quaternions, rotation matrix, you want to imagine the derivatives, AKA velocity accelerations, they're still 3D, because they still live in that tangent plane. Even if you're using a 4D quaternion or a 3x3 rotation matrix, you still want to have 3D velocity vectors, acceleration vectors, et cetera. And the mapping between those 3D derivatives and these 4D or 3x3, you know, attitude representations is what's going on in this kinematic stuff, right? I have to like figure out the mapping between the 3D velocities and the like 4D, you know, quaternion. And this is kind of what that mapping is. And the geometric picture for what's going on there is this thing about like, you're using a particular tangent plane to do all of the like derivative calculations in terms of omega and torque and stuff. And that's the body frame, right? That's the body frame corresponds to like the tangent plane to this thing at the identity. And then in order to like add stuff up and integrate, I need to rotate it down to where Q of T is now. That, yeah, okay. So I'm happy to talk more about this, but we're gonna keep trucking for now, unless anyone has any more burning questions. This stuff takes a lot to wrap your head around. So and also a bunch of the stuff I told you today is like non-standard Zach stuff that you won't find in any books. So I'm trying to give you the good little nuggets of years of my struggles with these things. So hopefully this is sort of making sense. I sort of struggled through this for a long time, and like this is what I came up with to explain it to myself. So yeah.
So does the orientation of the tangent plane is giving us information about the, or is there nothing that we can do from that tangent plane?
Yeah, so the tangent plane, I mean, it's literally sort of like, it's hard to, so this doesn't directly correspond to frames necessarily. Like this is a pretty abstract space that we're in here. But so it's not a direct correspondence, but like, yeah, I don't know how to say this any better. This is like this is a little weird. We're in like 4 dimensions and we're thinking about, it's the tangent plane at the current quaternion, right? Which is closely related to, like the quaternion is actually not a particular frame, right? So the transformation between 2 frames. But if it's the identity quaternion, that means the frames line up, right? And so that's kind of why this is nice. Is that the identity, certain things drop out and it becomes easier. So we kind of do all this math at the identity and then translate it to whatever tangent plane we're actually at. Does that make sense? Yeah, okay. Anybody else? Before we keep moving, did you have something?
So you're basically, what I'm getting is that if you measure it in the body frame,
Yep.
your measurements are identical with respect to that frame.
Yeah.
But now you have to, if you're trying to give your orientation in the initial frame, you have to account for the fact that the body.
Yeah. That's sort of getting there. This takes a while to wrestle with, and there's a lot of weird conflicting stuff in the literature. So I'm gonna make you do some more of this on the homework next time too, and hopefully you really just kind of have to wrestle with it and do it, I think, to some extent too, to like get the ideas in your head a little better. So, okay, this is weird stuff. This is not easy stuff to wrap your head around. And you know, it takes some work to get this stuff. But it's super practical and super useful, and it shows up all over the place. And way too many people who use this stuff don't understand it and just use code, you know, that they find and, you know, on Stack Exchange and stuff. And it's not, you know, not the best way to go. Okay, so now we're gonna kind of sort of switch it up a bit. We're gonna sort of next topic. So this is basically the end of our discussion of like attitude representations and attitude kinematics, right? So now we're going to start moving into dynamics, right? So like torques and actually how the thing moves rather than just thinking about the attitude itself, right? So we're going to start thinking about dynamics now. So the first thing we're going to talk about with regard to dynamics is kinetic energy. And this kind of naturally leads us into this idea of moment of inertia, which I think probably everybody's seen before, but I don't know if you've seen it kind of this way. This is sort of where it comes from. So if I want to figure out the kinetic energy of a rigid body, the simple thing to do, we can bootstrap all this on the definitions for particles. So the easy thing to do is just add up the kinetic energy of all the particles in the body, right? And this, right, sort of somewhat obviously is going to look like it's just 1/2 mv squared. So I'm going to write that like this. So sum over I, say 1/2 mi, and then ri dot transpose ri dot. So those r's are the position vectors of each particle in the body. And these are going to be consistent with like F equals ma and stuff, right? This is going to be in the inertial frame, these ri's. So I'm going to write the little decorations on this stuff when it's ambiguous. So this is simple. This is what we did before, right? Super easy. All I need to do now is sort of like sum these up. So what we're going to do next is we're going to plug in. So remember, right, these guys can't move around just on their own. They have to respect the rigid body sort of constraints. And as we talked about like last time or the time before, you can only do certain things to this collection of particles, i.e. you can translate it and rotate it, right? These are the rigid body transformations. So we're going to plug that in. So I'm going to write down R in the n frame. So I'm going to sort of belabor this and be super explicit about it. So to get this position of this particle in the inertial frame, what I want to do is rotate, and this is going to be a function of time, right? And I'm going to assume, you know, again, like at t0, the body and inertial frames line up or something like this, right? So I'm going to write these guys in a body frame, which is the same thing really as, you know, the inertial frame at t0, something like that. And then I'm going to also add on a translation vector, and that's going to be defined in the n frame. So this is, say, you know, rotating this guy from the body to inertial frame, and this is time varying. And then I'm going to add on this translation, you know, vector, right? I'm cool with that. And so let's make some notes. This is constant, right? In the body frame, because the distances between these guys are constant, these RIs in the body frame have to be constant. And this is a translation. Okay, so if I just do the chain rule on this guy now, I'm just going to take the derivative. So I get RI dot, I'm going to leave off some of the decorations now. It's Q dot RI in the B frame plus D dot, which is in the N frame. And this is equal to, anyone remember what Q dot was from last time? Q omega hat, right? So I'm going to just plug that in. I'm going to move this over a little bit so I can squish. Okay, so this is going to be Q omega hat. And remember, that's in the body frame. RI body frame plus, we're just going to call this now the D dot thing, just V for the velocity. Okay, clear, easy chain rule, no big deal. And remember, right, so these are all the particles, but this is just a single sort of, omega single translation for the whole body, right? So I don't have a sum over those guys. It's just one for the whole thing. Okay, so now we're going to plug that in. We're going to get T equals the same thing. I'm just going to explicitly say we've got MI. Now we've got Q omega hat body frame RI body frame plus V N frame. Transpose, same stuff. I'm going to cheat, be lazy. Okay, so we do this, and then I'm just going to like FOIL that, right? So now if I FOIL this, I'm going to get MI RI B Q. Oh, this is, I'm going to drop the B's on the omegas because it's just annoying to write. So omega, little omega is always in the body frame, actually for the whole class. So omega hat transpose Q omega hat RI, and this guy's transpose too. RI in the body frame. And then these guys, I'll keep going for a sec. So these guys cancel out, right? The Q transpose Q equals identity. And then I get two more terms. I get, and I'm going to write them in a particular way. So I get a 1/2 sum over the masses times V transpose V. Right. So remember the V's. These don't have eyes on them. There's only one for the whole body, so I can pull that out of the sum. And then the last term I get is weird and ugly, and it is Vn transpose Q omega hat sum over I MI RI body frame. So that's the cross term, right? So this is like this term is these guys squared, this term is these guys squared, this term is the cross term between these guys in the FOIL. Yeah. Oh yeah, good call, thanks. Okay, so what we're gonna do now is play a little trick. So this thing, what is this thing? I'm gonna recognize what that is. Think about statistics. What is that thing? Think about, it's basically like a weighted mean, right? If I have a bunch of RI vectors, this is a mean, right? And this is like a mass weighted mean. This is the center of mass, right? Times like a constant, the mass, right? But this guy is the center of mass of the body. So I can play a trick now. If I define my body coordinate system so that its origin is at the center of mass of the body, this term's going to be 0, right? Everyone agree? See that? Cool. So I'm basically going to say so I guess the origin. I'm going to rewrite this because I don't like the way that sounds. If I put the if I center the B frame at, oh yeah, if I put the origin, yes, this makes sense to me now. Sorry. If I put the origin of B frame at center of mass, last term goes away. Okay, and then what I'm left with is T equals 1/2 m, which is the total mass, V transpose V, which is exactly the same as a point mass, right? This is just the point mass term. And I get a new term compared to the point mass that looks like 1/2 sum over I, mi, ri, b, omega hat b transpose omega hat b ri. So this is a point mass term. This is a new rotation term. And there's interesting statistical connections here. This is basically a term related to the mean of the mass distribution. Turns out this term is almost the covariance. So this is basically what this is saying is kinetic energy of this thing, it's a quadratic thing, right? So it turns out, unsurprisingly, and it's integrated over the body. So if I think of the body like a probability distribution, like a mass distribution, I'm evaluating this quadratic function integrating over the mass distribution. So unsurprisingly, if I take that quadratic function integrated over the mass density, it's just like integrating a quadratic function over a probability density, which means it's basically first and second moments, right? It's only depending on first and second moments. So this is just like if I evaluate the expectation of a quadratic function over a probability distribution. It is the same thing, actually. And this is a little funky, but it turns out this is really closely related to the covariance. It's almost the same thing. Not quite, but almost. Okay, so so what we're gonna do now is rearrange that rotation term. And we're going to kind of pull some stuff out. So I'm going to use this fact. So I've got omega hat times Ri. This is equal to omega cross Ri, right? Body frame, which is also equal to, as we all know, Ri minus Ri cross omega, right? I can flip the cross product and pick up a minus sign. So that means this is also equal to cross product D matrixy thing times omega, right? So I can flip which one gets the hat. I can flip which one of these goes into the 3x3 skew symmetric matrix and which one I pull the vector out. And I just pick up a minus sign. Like that. Clear? Okay, so I'm going to just do that in the expression that we had. And we're going to end up with T equals 1/2 total mass V transpose V plus 1/2, and I'm going to pull the omegas out. That's why I did this. Omega transpose, and then the stuff in the middle, sum over I now, because I've got the RIs and the hats, that's all that stays in there. So MI, RI, hat, RI, hat, omega on the other side. And then this thing in the middle, now this is a constant matrix in the body frame, right? So body frame, these are constants, whatever, let's sum this all up. This is just a property of the geometry of the body, of the mass distribution of the body. This is called the moment of inertia matrix tensor, inertia tensor, whatever you want to call it. Technically, this is a matrix, not a tensor, because it's written in components in some frame. If you kind of imagine the abstract version of this that doesn't have, the like abstract vector version of this, that's a tensor when it's not in a coordinate frame, but we're going to call this thing J. And it's moment of inertia, we're going to go with matrix. And it's a 3x3 matrix, right? Sometimes you'll hear called a tensor. It is a tensor. The distinctions between those are a little fuzzy. They're even fuzzier in computer science. Okay, cool. So then at the end of the day, we're going to get this expression T equals 1/2 M V transpose V, where the V's are in the inertial frame. And then this rotation term, omega transpose J omega, where the omegas and the B's are all defined in the body frame. So this is a little funky, right? We got two different frames going on, but that distinction is important. The reason we do this, by the way, is that, and when we talk about rotations and stuff, this J, it's a constant in the body frame, but if I try to define it in the inertial frame, it's not constant anymore, right? Because these guys are time varying if I rotate them by Q. So thinking about the inertia in inertial frame is super messy and gross, so we don't do it. So we always kind of define dynamics and energies and stuff like this for the rotation part in the body frame. That's why. Because it's nice and clean in the body frame, and it's ugly and terrible in the inertial frame. Okay, questions about that? And yeah, there's like deep and fun connections to probability distributions. If you just sort of swap probability distribution for mass distribution, this kinetic energy thing is really a second moment of the distribution. This is basically, it's almost the same as covariance matrix. Fun bonus, if anyone goes and derives that connection, I'll give you some kind of fun bonus points or something. Okay. So let's see, final notes on this. J is closely related to covariance of mass distribution, and think of this kinetic energy as basically coming from like you get a mean term which tracks the center of mass, and like the covariance term that's tracking kind of the rotation stuff. Yeah.
I'm like following all of it. I think one of the RIs speaks to one transpose.
Oh yeah, for sure. Thanks. It should be this guy, right? Oh no, wait, did I do that right? Hang on, let me think about this for a second. I have to think now. So no, I think I transposed one of them. There's a trick in here. I think this is actually right for the following reason. So RI, so what's going on here is I flipped both of these around, right? And then I picked up, remember the transpose equals, you pick up a negative sign, right? So I can write a transpose on it, or I can pull out a minus sign. And I think I did the latter. So if I flip both of them, I've got transpose here. Someone check me. What did I do? I picked up two minus signs. So it should have a minus out front or a transpose on. Is that right? Kevin, can you check me?
I think so, yeah.
It needs a minus or a transpose, right? Or is it good there? So I flip both, still has a transpose on it. Yep, I did that. So I flipped, I guess what I'm saying is each of those flips picks me up a minus sign, right? So those cancel.
Yes.
So I should still have the transpose, or I should pull a minus out in this expression, right? Does everyone agree?
Yeah.
It should have, I'll put a minus sign out here. Cool, yeah, thanks for that. I think you're right. This is what happens when I do math at 2 in the morning, which I do way too often. Is everyone cool with that? Does that look right? Do we all agree?
I think they should get transpose this, right? Because you're flipping both of them.
Yeah, but remember this is this skew symmetric matrix.
Okay.
So the transpose equals, it's equivalent, right? I can put a transpose here, or I can put a minus sign up front. It's like exactly the same thing, right? So I just missed a minus sign effectively, because I was thinking about it that way. So yeah, Kev, double check for me. So okay. Okay. Any other? Did I screw anything else up? Do you have any other questions? Okay, cool. Keep trucking. Okay, so this is the kinetic energy story, and we've now defined this inertia matrix, which is super useful. Now we're going to actually do rigid body dynamics finally. And this is Euler's equation. Who's seen this before? Assume most of you. Not everybody. Okay. So here's what happens. So we now know how to do, we've seen, right, in this kinetic energy situation, translation and rotation decouple, right? They show up as separate terms, and that's kind of fun. And that actually turns out to happen in general for the dynamics of a rigid body. So I basically am going to be able to write down F equals ma for the center of mass translation stuff. And then I need a new equation for what's going on with the rotation part. And that's Euler's equation, which we're going to do right now. And this is, again, if we put the origin at the center of mass. That's important. So all of this assumes you get extra annoying cross terms, basically, if the origin is not at the center of mass. So we're pretty much always going to put the origin at the center of mass. Okay. So what we're going to do is the analogous thing for F equals ma, just like this conservation of angular momentum thing. Sorry, conservation of momentum. So F equals ma, remember the general story was derivative of the momentum equals the force. Right? And remember, these are all in some inertial frame, right? Got to be in an inertial frame for Newton's laws to hold. So this is momentum. This is force. It's going back to like day one now. So there's an analogous thing for rotations. It looks exactly the same. It is, we're going to write it with an L now. This is angular momentum. And the analogous thing for force is torque. And now we're writing these in the N frame, right? Just like the Newton thing. So this is angular momentum. This is torque. And we're going to define angular momentum kind of the same way we did as linear momentum. But remember, linear momentum is mv. But here we have this inertia matrix J replacing just the scalar mass. And that thing is only nicely defined in the body frame. So we're going to want to define this angular momentum also in the body frame, even though here it's in the inertia frame. So there's some weird frame mismatch stuff going on here. So in the B frame, we have angular momentum equals inertia matrix, which is always defined in the B frame, but I'll be explicit about it there, times omega in the body frame. And this is constant in B frame, like we said. So if I kind of rotate that into the inertial frame now to plug it in here, I get, you know, L in the N frame is just, I just stick a Q in front of it, right? And now I can plug that back in and just take a time derivative of it. So dln dt is equal to ddt of the thing I just wrote. And I just use the product rule here. So this guy, I get a Q dot, which is Q times omega hat, as we saw before. Or I guess I'll be super explicit about it. So this is Qj omega dot plus Q dot J omega B. And if I then sort of plug in again, I get Qj omega dot plus Q omega hat J omega. And then this thing is equal to torque in the N frame, right? Like we had here. This is just the tail end of that equation. So now what I'm going to do is just pre-multiply everything by Q transpose. So Q transpose, this is going to go away, and I'm going to get a Q transpose here, right? So this is now J omega dot plus omega hat J omega equals Q transpose torque in the end frame, which if I now just sort of simplify this down, this is just rotation from inertial body. So this whole thing is now just torque in the body frame, right? So now everything's in the body frame, which is kind of nice. And this thing, I'll write it as a cross product because I can, no big deal, equals torque in the body frame. Okay, so this is it. This is the famous Euler equation for rigid body dynamics. Okay, so that's it. That's the sort of analogous thing to F equals ma. It's a little weird because I pick up this cross producty thing in here, right? Instead of it just being, you know, this is sort of the ma term, this is sort of the F term, but I have this extra weird thing in the middle. And we'll go deeper in this later on, but this is kind of the simple, straightforward way to get this. It's just kind of this artifact of like writing this down in the rotating body frame, right? And I do that because I want to keep J constant in the body frame. So it's actually, this is the easiest thing to do. But at the end, you know, but it starts out, if you write it in the inertial frame, it is exactly the same as F equals ma, right? I just pick up this extra term because I translated that into the body frame. Okay, so now we can simulate rigid body dynamics. This gets you your, you know, you take the torques, you can integrate this and get omegas, and then we already know how to go from omega to Q, either quaternion or rotation matrix. Yep.
Is that a transpose Q above the equation?
Oh yeah, that should be on the other side. That was really dumb. Okay, thank you for pointing out all of my flaws. Okay, anybody else? Okay, cool. So now you can simulate a rigid body. By just taking this stuff for the rotation part and stacking it with F equals ma for the translation part. Okay, cool. How are we doing on time? We got 10 more minutes. I remembered what time we finished today. That's the first. So now we're going to do some more fun geometry stuff with this. Okay, so let's look at the unforced case, i.e. tau equals 0. Because some interesting things happen there that do not happen with the translation stuff. I hope we can get through this so I can do my fun demo that I brought to class. This should be a plus. Okay, so we got this thing, right? No torque. I can equivalently rewrite this in terms of the momentum. If I want to, which we'll use in a sec. So if I do that and I plug that in, I'm going to get L dot, right? Which is just this, the first term is just the L dot, right? Plus, now omega is J inverse L dot cross L, right? And then I can sort of slightly rewrite this as L dot equals L cross J inverse L. Simple enough. Just like messing with cross products and stuff. Okay, so now in the unforced case, I have two nice conserved quantities. The first one is energy, right? We already know that. The second one is the norm of the angular momentum vector. So norm of L is conserved, right? Conservation of angular momentum. We know that from the inertial frame case, right? I wrote dl in the n frame dt equals tau. So tau is 0, dl dt in the n frame is 0, right? So it's conserved in the n frame. This is in the b frame, so it is moving around because of that cross product term, which is a little weird, but the norm's still conserved, right? So I have this fact. So what does this tell me? This thing's a constant. What kind of shape does L trace out in the body frame? L lives on a sphere, right? So we're going to call this the momentum sphere. Okay. And then we also have conservation of energy. Which looks like in this stuff, L transpose J inverse L, right, 1/2. This is just 1/2 omega transpose J omega. I plug in, omega equals J inverse L. I get this thing. So what shape is that? So this guy, true norm constant, sphere. This thing, this quadratic form is constant. What shape does that make? Yeah? Sorry? No, it's a level set of a bowl, right? Which is what shape? It's an ellipse in 2D. This is in 3D though, right? So this is an ellipsoid. If you like statistics, think about this as a like a covariance matrix, right? And then this is a level set of a covariance, right? So it's an ellipsoid. Does everyone get that? Let's see how that works. Literally what it is, right? This would be just identity in here. So it's L transpose L is a sphere, right? If I stick a matrix in the middle, I can stretch the sphere in a couple directions and I get an ellipsoid. Okay, so this says lies on energy ellipsoid. So then what this tells me is that for all t, L of t has to lie on both of these manifolds, which means it's going to lie on the intersection of them. So if I have this ellipsoid and I have this sphere, they intersect at some curve, and the trajectories are just the intersection of this ellipsoid and this sphere. Does everyone see that? Like, that makes sense? And I'm going to be terrible at drawing this, so I'm not even going to try. I'm going to just do like this kind of picture, which is terrible. Apologies, but I'm going to show you some better pictures in a minute. Okay, cool. So that's fun. So next thing to talk about is equilibria of this thing. So I have equilibrium points. Remember, that's where, in this case, this is a weird case, right? So it's not the full state. We're just looking at the angular momentum or the angular velocity, whatever. So we call these equilibrium spins, right? So this is where the spin vector, the omega vector, or the angular momentum vector isn't changing, right? So it's still spinning, but it's spinning about at a constant speed about a constant axis, not doing anything else. So looking at these equations up here, where's L dot going to be equal to 0? So I want L dot equal to 0. When does that happen? So when does a cross product equal 0? Louder. When they're parallel, right? So this is saying that L is parallel to J inverse L, or equivalently, omega is parallel to J omega, or equivalently, angular velocity and angular momentum are parallel. Everyone get that? So this we can write when L cross J inverse L equals 0. Similarly, omega dot equals 0 when omega cross J omega equals 0. So this says omega parallel to L. So writing that another way, which is very suggestive, omega equals some lambda times J omega, right? That means parallel where like lambda is some constant, right? Some scalar. So now with that hint, when does this happen? It's a huge hint. Yeah. Yeah, so whenever omega is an eigenvector of the inertia matrix, this is true, right? Because it just gets rescaled, it doesn't get rotated at all. So there are how many equilibria for a spinning thing like this? Not 3, actually. So it's either direction, right? So if I think about this momentum sphere, it's going to be plus or minus each eigenvector. So it turns out there's 6 total equilibria. Okay, so cool. 6 total. Sorry, say that again. E- They're related, but there's more going on here. We're going to get to it. It's going to take us, we need some more math machinery to like kind of get some more deeply into this thing. Which is, kind of, we will get there. Yeah, so eigenvectors of this thing, 6 of them. I'll draw a picture in a little bit. So what I'm going to do next is we can actually talk about stability of these things. Yeah?
I'm sorry, where did the equilibrium condition come from?
Just that the L dot equals 0 or omega dot equals 0. So omega, yeah, so like, f of x dot equals 0 is the definition of the equilibrium here, right? So here I'm just looking at the spin, i.e. I'm just looking at the angular velocity or angular momentum dynamics. I'm not looking at the rotation matrix or quaternion dynamics, right? So those are still changing.
Oh, sorry, what's the meaning? Why are those equilibrium? But why are we taking equilibrium?
These are so-called equilibrium spins. They're equilibrium points on the momentum sphere. Right? So if this thing's spinning, no force, external forcing, it's spinning around, it's tracing out some trajectory on the momentum sphere, right? Turns out, in general, it's going to wiggle around and move around on the momentum sphere. There's 6 points where it will stay put, theoretically, right? There's 6 equilibrium points on this momentum sphere corresponding to the eigenvectors of the inertia matrix. Is everyone clear on that? Okay, so now what I'm going to do, oh, are we at time? We are at time. Okay, so we'll do this next time.